Pay attention to the definition of onto when you're trying to prove that a function is onto. The definition is for all members of the codomain, there exists a member of the domain, blah, blah, blah. So the first line of your proof should be let y be an element of the codomain, and then you have to define an element of the domain. I saw a common error when I was reading through the homeworks. Let y be an element of the codomain, then y equals 2 minus 3x. What is x? X is not defined, and even if it were, you're coming out and declaring that y is equal to f of x, and that's what you're trying to show. So writing something like this is just completely backwards, all right? Instead, we're going to start with an arbitrary element of the codomain. So again, the first line is good. Let y be an element of R. And then we need to find specifically the element of the domain that's going to get mapped to y. I can figure out what it's going to be with some scratch work, that's fine, but the scratch work is not part of the proof. So y equals 2 minus 3x is a perfectly good way of starting your scratch work, because you got to figure out what x should be in order for that equation to be true. But that is all written off to the side. And just in general, all the scratch work that goes into the proof, just don't even include it in your homework or exam at all. Do it off to the side, and then come back to the main body of the proof and write nicely. So I know from my scratch work that setting x equal to 2/3 minus 1/3 y, that'll do the trick. So I set x equal to that number. Now I've declared the variable x. It's not dangling or anything like that. And I just make the observation that it happens to be a number that's in the domain. And when I plug it through the function g, so g of x, look what happens. I put in 2/3 minus 1/3 y, and everything cancels out, and I get y out. So this is the proof that g is onto. I've started with an arbitrary element to the codomain, and I found a specific member of the domain that gets mapped to it. Okay, if I want to prove that a function is one-to-one, I also need to pay attention to what the definition of one-to-one is. So here's number 31. Off to the side, let me remind you what it means for a function to be one-to-one. It's got a precise definition, so when I want to prove one-to-one, I need to follow that precise definition. I want to make a mathematical argument here. I don't want to just put together a couple intuitive sentences about why I think this function is one-to-one. I have to have math in there. So as a reminder, function g is one-to-one if given any two outputs that happen to be the same, they must come from the same input. One way of writing that is given any x and y in the domain x, if f of x equals f of y, then x equals y. That structure guides your proof. Your proof needs to start then with let two elements of the domain and suppose that the function values that those two members of the domain are equal, and so on. So for this particular function, the domain is a collection of ordered pairs. So I'm going to suppose that I have two elements of the domain whose outputs through this function happen to be equal. So suppose n1, m1, and n2, m2 are elements of the domain such that gn1, m1 equals gn2, m2. So now I get myself a mathematical equation to work with. So I know the definition of g is 3 to the n, 6 to the n, so let me write this down. I get myself an equation, 3 to the n1, 6 to the m1 equals 3 to the n2, 6 to the m2. Now I have to reason that this gives me that the n's are the same and the m's are the same. Right now, it's not immediately apparent because I don't have prime factorizations. So manipulate it slightly so that you're looking at a prime factorization on the left and a prime factorization on the right. The minute you have that, since you know prime factorizations are unique, you can conclude that there are the same number of 3's on the left and the same number of 3's on the right, and 2's as well. So be careful with what you can conclude from that. You can't immediately conclude that n1 equals n2. All you can immediately conclude is that n1 plus m1 is equal to n2 plus m2, and m1 equals m2. So same number of 3's gives me the first equation, same number of 2's gives me the second equation. You have to put those two equations together to further conclude that n1 equals n2. make sure you understand each of the lines of that proof. And just overall, I made this video because I want you to stay focused on the actual definitions of the properties that you're trying to prove. In the case of onto and one-to-one, there are very specific mathematical formulations of those properties, and you need to follow them carefully when you're trying to prove them.